Embedded systems are everywhere. They are the brains inside your smartphone, your car, and even your microwave. These systems rely on specialized software to interact with the hardware. This is where Embedded C comes in. Embedded C is a programming language perfect for these resource-limited devices. It gives developers precise control over hardware components. A key aspect of this control lies in understanding control structures. Control structures dictate the flow of a program. They determine the order in which instructions are executed. This is crucial for reacting to sensor data, controlling actuators, and managing system timing. Without control structures, embedded programs would be limited to executing instructions sequentially. This would make it impossible to create responsive and interactive systems. In the upcoming sections, we will delve into the different types of control structures available in Embedded C. Imagine you're programming a thermostat. It needs to turn on the heater if the temperature falls below a certain point. This is where conditional statements come into play. They allow your program to make decisions based on specific conditions. The most common conditional statement is the if statement. It checks if a condition is true. If it is, the code within the if block is executed. Otherwise, the program skips to the next part. If temperature 20, we can add an else block to the if statement. This else block executes only if the if condition is false. If button pressed, else. For multiple conditions, we use else if. This allows for a series of checks, making the decision process more specific. If speed 30, else if speed 60, else. Conditional statements give embedded systems the power to respond dynamically to their environment, making them adaptable and intelligent. In embedded systems, we often need to perform the same task multiple times. Think of a heart rate monitor that constantly samples data. Loops are control structures that allow us to repeat blocks of code. The for loop is perfect for repeating a task a specific number of times. It has a counter that keeps track of iterations. For int I equals sign 0, I 10, I++. This code snippet would read sensor data 10 times. The while loop repeats a block of code as long as a condition remains true, while sensor value threshold. A do-while loop is similar to a while loop. However, it guarantees that the code block executes at least once. This is because it checks the condition after each iteration. Do-while transmission not acknowledged. Loops are essential for tasks like data acquisition, motor control, and communication protocols in embedded systems. Imagine you're driving a car and suddenly you need to brake. You don't wait for a scheduled brake. You react immediately. Interrupts in embedded systems work similarly. They allow the microcontroller to respond to critical events immediately. An interrupt is like a hardware signal that tells the microcontroller to pause whatever it's doing and handle a high-priority event. This event could be anything from a button press to a sensor exceeding a critical value. When an interrupt occurs, the microcontroller jumps to a special function called an interrupt service routine, ISR. The ISR handles the interrupt, performs any necessary actions, and then returns control back to the main program. Void button SR / handle button press. Interrupts are vital for real-time responsiveness in embedded systems. They ensure that critical events are handled promptly, even if the microcontroller is busy with other tasks. As embedded systems become more complex, managing the different states and timing requirements can be challenging. State machines and timers are powerful tools that help us design well-structured and time-aware embedded software. A state machine represents the different states a system can be in, such as idle, running, or error. We use transitions to move between these states based on events or conditions. In embedded C, we often implement state machines using switch statements or function pointers. Switch statement example: switch current state, case idle / handle idle state break, case running / handle running state break. Timers provide accurate timekeeping in embedded systems. We can configure them to generate interrupts at specific intervals. These interrupts allow us to execute tasks periodically, like updating a display or checking sensor readings. Timer interrupt example / configure timer interrupt / void timer SR / update display. State machines and timers provide a structured approach to managing complexity in embedded software. They enable us to create systems that are modular, maintainable, and predictable. Embedded systems often operate with limited resources, such as processing power and memory. Optimization is crucial to ensure that our code runs efficiently within these constraints. One common optimization technique is to avoid using recursion whenever possible. Recursion, while elegant, can quickly consume memory, especially in resource-constrained environments. For example, consider this recursive implementation of a factorial function, int factorial int n. If an equal sign = 0, return 1, else return an asterisk factorial n1. Now compare it to this non-recursive version, which is more efficient, int factorial int n, int result = 1, for int I = 1, I = n, I++. Result asterisk = I, return result. Another area for optimization is dynamic memory allocation. Dynamically allocating and deallocating memory can lead to fragmentation and unpredictable behavior. It's often best to use static allocation or custom memory pools in embedded systems. For instance, instead of dynamically allocating memory like this, int size of int, you can use static allocation, which is more efficient, int data 100. By optimizing our code, we can ensure that our embedded systems perform well, even with limited resources. Let's combine everything we've learned to create a simple embedded system that controls an LED based on a button press and a timer. Hash includes // example microcontroller, header file // define LED, and button pins hash define LED underscore pin P1, 0 hash define button underscore pin P1, 1 // global variable to track LED state int LED state = 0, // interrupt service routine for button press, hash pragma vector = port 1 underscore vector underscore interrupt void port underscore 1 void // toggle LED state on button press, LED state = LED state // clear interrupt flag P1 IFG and =tilde button underscore pin // timer interrupt service routine hash pragma vector timer 0 underscore a 0 underscore vector underscore interrupt void timer a void // toggle LED state every 500 milliseconds if LED state LED underscore pin = 1 else LED underscore pin = 0 int main void // stop watchdog timer WDT steel = WDTPW vertical bar WWD told // configure LED and button pins P1 DR = LED underscore pin P1 dir and = tilde button underscore pin P1 ren = button underscore pin P1 out = button underscore pin // configure button interrupt P1 IE = button underscore pin P1 IES = button underscore pin P1 IFG and = tilde button underscore pin // enable interrupts globally. BIS SR register GIE // main loop while 1 // sleep or do other low priority tasks. This example demonstrates how conditional statements, loops, interrupts, and timers work together to create a simple but functional embedded system. Even experienced embedded developers encounter bugs in their code. Debugging is the process of identifying and fixing these errors. Here are some common debugging techniques for embedded systems. Using a debugger. A debugger is a powerful tool that allows you to step through your code line by line, inspect variables, and set breakpoints. Printing debug messages. You can use a serial port to print messages from your embedded system to a computer. This is helpful for monitoring variable values, program flow, and the status of different components. Using an oscilloscope or logic analyzer, these tools allow you to visualize the electrical signals in your circuit. This can be helpful for debugging timing issues, interrupt problems, and communication protocols. Code review and testing. Having a colleague review your code and thoroughly testing your system can help catch errors early on. Debugging is an essential skill for any embedded developer. By using the right tools and techniques, you can quickly identify and fix errors in your code. Mastering control structures is fundamental to becoming proficient in embedded C programming. We've covered the essentials, from conditional statements and loops to interrupts, state machines, and timers. Remember, Practice is key. The more you experiment with these concepts, the more comfortable you'll become. Start with small projects and gradually increase their complexity. As you delve deeper into the world of embedded systems, you'll encounter new challenges and opportunities. Embrace them. The field is constantly evolving, offering endless possibilities for innovation and creativity. Now that you have a strong foundation in control structures, you're well on your way to creating amazing embedded systems.